Today we're going to take a look at what's going to feel a little bit, at least at the beginning, like a deviation from what we've been doing. It's called Pascal's triangle, but it has direct relationship to exactly what we have been doing, and that will come about in our work today. So to start with, Pascal's triangle is an unending triangular array of numbers. It was written by Pascal, mathematician, in 1653. But as with many of the things in mathematics, it's credited to someone who finally wrote it down, but it was known far earlier than that. There's actually evidence that shows it was studied in China and India as early as 1100 or earlier. So this goes back quite a bit. We're looking at 1,000-ish years old kind of thing. So you may have seen Pascal's triangle before. You probably haven't seen it used the way we're going to use it. But I'm going to show you how we sort of can develop it and how it extends to be unending. Although obviously if it's unending, we can't write it all out, so that's not practical. But Pascal's triangle actually, do I have two of them? Oh, I had a spot to do it here. Okay. Starts out with a 1 at the top of the triangle we're going to create. And then there is a 1 and a 1 sort of off-centered from the initial 1, so in a triangular kind of shape. What happens on the edges is that they continue to be 1s, and the number in the middle here will be a 2. And I want to write out maybe a couple more rows before I show you the connection between the rows and what happens between them. So there's still a 1 on these edges, and then these are both 3s. And then there's a 1 on these edges, and we have a 4 and a 4, and in the middle we have a 6. Okay, so this is the first few rows of this. So a few patterns to sort of draw your attention to. Along each of the diagonals along the edges, they're all 1s. They're always going to be. And if you go along the second diagonal, you see that it goes 1, 2, 3, 4. The next one's going to be 5, and 6 all the way down. The same thing for this other diagonal. Another piece that changes, but there is a relationship, is you see this 6 sort of showing up in the middle, and you might have been like, well, where'd this 6 come from? It's actually, and this is true for all of the triangle, the addition of the 2 above it. So if you take a look at the 6 to the 2 above it, there are 2 3s, 3 plus 3, 6. So if we were to sort of keep that in mind, we can create the next row. This one would be a 1. This one will be a 5 because it's the next number, but it's also a 5 because 1 plus 4 is 5. Everybody see that? So this one, this 4, and this 6 is going to make this number a 10. And then I have another 6 and 4 over here to give me another 10. The 4 and the 1, or I can use the fact that I'm along this diagonal, gives me a 5. And then a 1 on the outside. So what we're doing is called a recursive process. It means you need to know the row before you can get the next row. Right, so I can't say, okay, we'll do like row 16 now, and you just be able to jump down there and do it. You can't do that. But we can develop the next row, and we could do this indefinitely if we needed to. Let's do one more row so I can show you a couple more connections that we're going to make. So this one's a 1 and then a 6. What would the next entry be? 15, yeah. The 5 and the 10 make it a 15. And then what? 20? Mm-hmm. And then we have 15, 6, and 1. And you'll notice, of course, too, though I didn't mention it, there's symmetry, right? Once you get to the middle of whatever the row is, it either doubles in the middle or it starts decreasing in it and it mirrors the other side. So either way you look at it, every row is symmetric from the left to its right. So a few things about this. If you take a look, we actually call these by rows. We'll see if I can keep them lined up well enough. So the rows are I'm going to write it on the left. This top row is considered row 0. So I'm on this row right here. I'll try maybe, I think highlighting yellow, I can do it that way. This would be considered row 1, and it's the row that has just the ones on it only, the 2 ones on it. And then we would have row 2 and row 3. I'm going to write them all out. Another way that you can keep in mind of which row you're on is that the row that you're on corresponds to the first non-1 entry, right? So row 6 has the 6 as the first entry after the number 1. They've always got a 1 at the beginning, but it'll be row 6 that has the 6 in it. Row 10 would have a 10 in it as its second entry, that kind of stuff. So you can kind of keep track that way. On the other side of my triangle, what I would like to write out is what the sum of the row is. In other words, if I were to add all the values on the row together, what would I get? Let me shift that up just a little bit. So obviously, the first row, which we called row 0, would have the value of 1 because there's just a single 1 on the top. What would the second, or we'll call it row 1, have?
2.
A 2. And then how about row 2?
4.
It's 4. How about row 3?
8.
It's 8. We're going to finish all of our rows out. Row 4, 16. Row 5,
32.
and we'll do row 6. It's 64. So let's look at these summations that we got over here. So if we were going down this, do you notice a pattern from row to row on the summation? What's the pattern?
It's just being multiplied by 2.
It is. It's being multiplied by 2. So if I wanted to do the next row and I didn't want to do all the adding of things up, it's probably going to be
64 times 2.
64 times 2, which is 128, right? So yes, that is the pattern that's going over there. Now, defining it the way that Cooper did is a recursive formula, where you say, I need to know what the row is before to get the next row. Graydon?
The numbers in the middle, like the 2 10s and 2 30s, that's the only time, or I guess that's the only time whenever you put like the 2 numbers like add together in the middle.
So it's the only time that you have to, but it's not the only time it works. For example, the 5 and the 1 here make the 6. But we don't have to think of it that way. We could also think of it as the pattern going down the diagonal. But it's true for all of them. Yeah. There's one other way that we can think about the summations beside it being a recursive formula, which is that I multiply by 2 to get the next row. You can also think of that summation row as powers of 2. So for example, this over here is actually 2 to the first. I'll keep just using black. This one's 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, and 2 to the 6th. The reason that might be a nice way to think about it is because if you take a look as you go down, the row that you're on, row 6, corresponds to the power of the summation 2 to the 6th. The reason a formula like that's nice is because I don't need to know what the row was before to know what the summation is. So I could simply ask you what's the summation on row 10, and you'd know it. It's 2 to the 10th. So thinking of it from that perspective has its own sort of benefits too. Okay, are you ready to see what the connection is to what we've been doing? Absolutely, right, Quentin? Of course, what's going on here? Okay, so all of the values inside Pascal's triangle are combination values. How interesting. So let me show you what I mean. The one at the top is actually 0C0. The next one is 1C0, and I have 1C1. I have 2C0. In the middle it's 2C1, and then I have 2C2. I'll write a couple more rows out. 3C0, 3C1, 3C2, and 3C3. 4, 4C0, 4C1, 4C2, 4C3, and 4C4. And we could continue this down as far as we'd like. So let's just try one. We'll do something on the last row that I did. Let's try the one that's in the middle here. This one, like 4C2. Okay, let's actually calculate 4C2. So 4C2, from what we did in lesson 10.3, says I should have a 4 factorial on the top. I should have 4 minus 2, which is 2 factorial on the bottom, and 2 factorial. So that's 4 times 3 times 2 factorial, which matches one of the 2 factorials, 2 times 1. Two factorials cancel, this 2 and this 4 reduced to a 2, and I end up with a 6. Okay, so that's what it should be. That's what 4C2 is. But take a look where we are. We are on the 4th row, and we're on the 1, 2, 3 location in, so it always starts at 0. So if you go over here on the 4th row, 1, 2, 3 location in, I'm at 6. And it works every single time. Which means if you have an elaborate enough written out Pascal's triangle, there's no need to do a calculation to find 4C2. You can simply read it straight out of the triangle. So we're going to practice doing that. I think I might need one more row for the examples I have. No, I think I'm actually okay. So let's take a look at a couple of examples. This one says that we're going to look for 6C3 and then number 2 is going to be 8C6, but we're going to read it straight out of Pascal's triangle. So could I write it all out? Yeah, I could. Right, I could find 6C3 the same way that we did in the last section, but we can actually do it quicker by using Pascal's triangle. So the 6 here at the beginning tells me I'm on row 6, right? And the 3 tells me that I'm 3 entries after the number 1. That's what it really tells me. So over here, I find row 6. Okay, so row 6 is my bottom row. And I need 3 entries after the number 1. So here's the number 6 is the first entry after the number 1. Then I have the number 15. Then I have the number 20. Okay, so the answer to the first one is actually 20. So this here tells me I'm on the 6th row. And this says that I'm at the 3rd entry after 1. The entry, the number 1, is considered the 0th entry. So it's the 3rd entry after the number 1. Now my picture did not go far enough to do number 2. Okay, I went fine for number 1. I went down to row 6, but I need to go down to row 2 for number 2. I wrote down to row 8 for number 2. So we're going to go over here, and you guys are going to help me fill in the next 2 rows that I don't have filled in. I'm going to move this over a little. All right, we're close enough. All right, how about row 7? So somebody tell me some entries. I'll start. 1, 7, 21, 35. Yep. And 1. Okay, so I won't do any more summations over here, so it's okay that I'm going to run out of space. But how about row 8? 1. 8. 28.
56. 56. Oh, no,
70.
56.
Yep.
28. 8. 21.
Okay, everybody good? Okay, so pause for a moment. I won't speak and I won't tell you the answer. I would like for you to figure out what 8C6 should be based on the work that we just filled in. C6.
So we can do this with any of these problems.
You can. It becomes sort of impractical if we did something like when we were doing like the card games where there's 52 cards. You would not want a Pascal's triangle to go down to 52. But with values that are in like units digit values, like up to 8, like you already have a triangle for it. So yes, you could do it for
Say we
anything.
made one mistake crazy.
Yeah.
We used to use that on.
Yep,
on the test.
you could, absolutely. Mhm.
Because that was gonna be trouble last time. I don't know what it was. I couldn't do it.
Okay.
So,
Yeah, you can. All right, so what is 8C6? What should it be?
28.
It's 28. So it's the 6th entry after the number 1. So here's 1, 2, 3, 4, 5, and 6. It's 28. Cool? Yeah, it's an interesting connection. All right, so we're going to actually do a like an application type problem where the computations will still send us back to the Pascal's triangle to find our values. So our example that we're looking at now says that we're going to have a committee of 3 people. Remember, anytime you see the word committee tells you it's a combination. We've seen that before, but just a reminder, this means a combination, which it needs to be, otherwise we wouldn't be able to use Pascal's triangle. There's no permutation values in Pascal's triangle, it's the combination values. Okay, so we have a committee of 3 people. It's being selected from 7 women and 3 men. Find the number of ways of obtaining each result. So it says exactly 3 women. So all 3 of the people selected have to be women. How many women are there to select from? 7. So this is actually asking me to do 7C3. Does that part make sense? 7 women, choose 3 of them. And it's a committee, so I've got a combination.
Does this work with the permutations as well?
You can't use Pascal's triangle for permutations. You can only use it for combinations. Yeah. So 7C3, what would that be? 35. So it's the 3rd non-1 entry on row 7. That's a 35. So this one is 35. How about exactly 3 men? What is the notation I would be looking for on that one?
3C3.
Okay, because there's only 3 men, right? So 3C3. So I'm on the 3rd row. What would that be?
How do you know when it's C31 or C30 since it's only the 3 people, only 3 guys?
Okay, so the first number tells you how many you can pick from. There's 3 of them, right? And the second number tells you how many you're choosing. So the first the first 3 that's coming into play is from this part where it says there's 3 men. The second 3 that's coming into play is coming from up here where it says we're selecting 3 people to be on the committee. Okay? All right. What is 3C3?
1.
It's 1. It's the last entry actually on row 3.
So
Yeah.
we skipped the first one, but the answer can still be 1.
The answer can still be 1. We're just not counting. The first just considered sort of like, well, if you take a look over here, actually, notice all my values over here are the C0s. So it's the 0th sort of diagonal. And so we're starting with the first diagonal that's then on 1 diagonal. Yeah. So this one actually is, you're right, the number 1. So the answer can be the number 1. This one says exactly 1 woman. Okay, so if there's exactly 1 woman, how would I go about selecting that woman? What would the notation be for that? 7C1, that's right. So if I wanted to select 1 woman from among 7, that is 7C1. But that does not create a committee of 3 people. That's a committee of 1 right now. So if there's 1 person on the committee already, I still need 2 more, right? And the 2 more that I need can only be from among the men based on the way that this is set up, correct? So I would need to select from among the 3 men 2 more people. So I end up with 2 pieces of combinations, but notice the 2 here and the 1 here still add up to me choosing 3 people on my committee. Right? Still going to have a 3-person committee. 7C1 gets me the 1 woman. 3C2 gets me the 2 men on the committee. And we can use our triangle again to do that. So 7C1. What is 7C1? It's 7. Whoops. And then I need 3C2. Yeah, 3C2 is actually 3. Everybody find that one okay? Okay. And 7 times 3 would be 21. So there's 21 different combinations of people that I could pick to make a committee that had this structure. How about exactly 1 man? So what would that look like?
3C1,
3C1, because there are 3 men to pick from. And then what?
7C2,
7C2. And again, notice I am selecting all 3 people, 1 and 2. So I need 3C1. What is 3C1?
3,
It's 3. Mm-hmm. And then I need 7C2.
21,
Yeah, it's 21. And then 3 times 21 would be
63,
63. Now, when you looked at those 2 problems, you might have thought, well, they're probably going to be the same. One of them has 2 men, one of them has 2 women, right? I mean, it's the same structure. The reason it ends up being so different is because there are more women from which to pick. And that's what's causing that difference to happen, is because I have more different ways that I can select the 2 women than I can select the 2 men when there's only 2 men in my committee. Any questions on that? All right.